Okay, I had a question about working example 9.1 from Shigley. It is a little bit confusing. It's got a couple of drawings down here of what's going on, and maybe it's difficult interpreting what all of this is telling you and exactly how it all fits together. So I thought we would go through that and see if we can solve example 9.1 following what's already laid out in the book. So this is the 10th edition of Shigley. Example 9.1 is talking about welding. And the problem is telling us that there's a 50,000 Newton load applied in this direction on some kind of circular feature. It tells us that there's a 200 millimeter channel, so that's down in here. And there's these plates on the side and this tubular thing in the middle. This little diagram down here is kind of showing us the weld group that we're going to be dealing with. And then it goes through the calculations of direct shear, secondary shear, combines them together, and finds the worst case shear stress. So I thought probably what would help us first is to try and figure out what is this even telling us. So let's go over to Fusion. This is Fusion 360, and look at what is actually going on here. So this is the 3D version of the channel, so the gray channel down here at the bottom. The plates on the side, so I colored them red. Here's that tubular feature. So if we looked at this view is basically telling us what is going on right here. And then if we look at this view, this one has perspective turned on, so you can kind of see the sides coming in. I suppose if I turned that off, you would, I don't remember exactly where to go to turn that off now. Let's see, I think it's in the camera. Here we go, there's orthographic. So there is the view that's given right here. This view isn't really one of the model, it is the weld group. So what I did for that is, let's go back to Fusion, get the book out of the way. What I did for that is I kind of went in and colored them green. So you can kind of, I really don't like the orthographic camera. I'm going to go back to perspective, it kind of messes with me. So here is one of the welds on the back side, and there's another one on the other side. And then there's welds along the edges here and here, and then on the other side also. So there's actually 6 different welds. Your group does combine your book does group them into this weld on the top and the weld on the side and the side. It groups them into one C shape. That's what this is down here. That is those 3 welds put together. And so, this corner over here kind of gets weird, because when you look at what's really going on, and it doesn't even really show up too well in here. So, there would be some welding that goes across this little gap right here to connect them together. I didn't bother trying to model that in Fusion, but it would technically, there would be some weld going across there that we're kind of ignoring that, although that is a corner, and usually the corners of weld groups are the important parts. So we're not going to completely ignore it, because the corners are usually pretty important in the weld groups. So the ends down here and the corners are going to be the places of interest that we're going to try and calculate the shear stress. So we'll calculate down here. I think your book calls this point A. Yes, point A, and then point B is over here. Point C is this corner. Again, it would kind of go across the top over here. I just haven't modeled it in the software. And then point D is over here. And so that's kind of what's going on. The 50 kilonewton load is applied in this direction, kind of pushing on this brown bar. And one of the things that's in the problem solution in the book is that they look at one plate. And so they make the assumption that a total of 50,000 newtons is applied to this bar in the middle, and 25,000 of it gets dealt with one plate, and the other 25,000 gets dealt on the other side. So we're only going to look at 25,000 newtons on one of these plates. Although I think Yes, your book does. In fact, let's look at where it points that out. I think we're done with fusion anyway. We can probably get rid of it. See how it's got 25,000 newtons? That's what's going on with the 25,000, is it's having that 50,000 newtons between the two plates that I've drawn, the two red plates. All right, so we've gotten that. We won't totally get rid of fusion just in case we need to look at it again. I've got Mathcad going over here. So let's start with, let's input some variables. So let's say that we know force is going to be 25 kilonewtons. So we know that. We also see in the book, it tells us, let's look at our book again. So it tells us a couple of things here. One is that it tells us the weld sizes. We've got 6mm fillet welds in here. This one down here is telling us we have 6mm fillets on both sides of the arrow. So that refers to this side, and then the other side of the arrow is way over here. So we're talking about the other side of the plate in that case. So 6mm fillet weld here, 6mm fillet weld here, and then this one is indicating the 6mm fillet weld across the back here. This little dotted line across here is referring to the fact that this is a channel, and so if you really get a ruler out, you can see at the bottom here lines up with the dotted line at the bottom, and the top of the channel lines up with this upper line here. And so it's just showing the hidden line of the channel being hollow there. There's plenty of dimensions on this one that we can look at later, but I assume that you can figure out where all these dimensions, well, we haven't talked about this 110.4 yet. We'll talk about that one in a minute. But all these other dimensions are just sizes of the channel. They're given in, you know, how high is this little bar or this tube above the surface of the channel, things like that. Let's create our version. Now, I may do something slightly different with this. Actually, I probably should call it exactly the way that they did here. So what we did in our examples earlier, we took the 25,000 newtons and translated it down to the centroid of the weld group as a force couple. So we basically take the 25,000, put it down here, and add in the moment that would need to exist to replicate the effect of the 25,000 newtons up here. What they've done is basically created a free body diagram of the weld. So here's the weld, and there's 25,000 newtons applied through the weld, but it's coming through this plate. And these are the reactions to that 25,000 newtons. So they did it a little backwards. It doesn't really change any magnitudes or anything, but it would change directions of things. But again, all the difference would be is, are you looking at what the plate is doing to the weld or what the channel is doing to the weld? And so it doesn't actually matter in this case, but they did do a little bit different than what we did the last time we solved one of these things. And it's okay, either way is okay. So let's create our version of this thing, just because we're going to need that. So we've got the weld group. They draw it as a they draw it as a you know, a solid thing. I'm not going to worry about making it solid. They put the reactions in there, the 25,000 Newton force. Actually, first, we probably need to find, you know, where's the centroid of this weld group. So to do that, we need some of the tables over here. Now, we have two of these tables, remember. We have table 9.1 here, and we have table 9.2 over here. Well, we're kind of zoomed in there. Let's zoom out a little. All right. The difference is table 9.2, if you look at the top of it, it tells you bending properties. So 9.1 is torsional properties. So we have to pick the table that makes the most sense with what we're doing. The way we've got this thing set up, it's wanting to twist or torque and translate that way, I guess, depending on which way you're looking at it from where the external force is applied. But that external force, if that 50,000 newtons is pushing up here, then it wants to translate this thing and it wants to torque this thing. It doesn't want to bend it. So we need table 9.1 with the torsional properties. And they have this, case 4. Now it's not oriented the same way. It looks like, a capital letter C, whereas we have, this shape, which is rotated 90 degrees. So we do have to keep that in mind. We need to look at it this way and make sure we're using the correct dimensions that we're interested in. We kind of know what they've labeled as Y bar, that's going to be in RX direction, assuming X is horizontal. We want to know what X bar is in this picture because that's in our Y direction. So we need to solve this equation, b squared over 2b plus d. We need to solve that to get this dimension. So this dimension is going to equal b squared over 2b plus d. And the dimensions are, b is this dimension, and d is this dimension. All right, so we do have to make sure that we translate their picture, rotate it mentally, or draw it, rotate it however you want to do it. We just need to make sure we're using the right numbers in here to match up with what we need. Okay, so for us, we need to look at our diagram here. This is shown that B is 56 millimeters and D is shown to be 190 millimeters. Okay, I think that can lead us over to Mathcad really quick. So B is 56 millimeters, D is 190 millimeters, and X bar, we'll just do it this way, is equal to B squared over 2B plus D. And we get a value of 10.384 millimeters. Let's see if they, all right, so in the book, that is right here, 10.4, 10.384 is what we got, so they just rounded a little bit. So that's solving this part. Now they went ahead and had already solved the direct shear before they did the Centroid. That is totally fine. I normally want to do the Centroid of the weld group first, or the bolt group, or whatever it is, and then do the direct shear, but it really makes no difference. That's just what they did. Versus what we're going to do now, we can go and find, well, let's write this down. This was 10.4, let's use the number that they used, millimeters. The direct shear, now what they have got here is, remember there's an external force. This is why I don't like this particular method, is because they only show the weld group, and the 25,000 newtons is just kind of floating up here. No, too far up there. It's just kind of floating up there, which is what you have to realize, that it's actually applied to the tube, which is connected to the red plate in our model, and the red plate is welded through this weld group to that channel. So that's how it's all connected together. So we obviously have a reaction here of 25,000 newtons to keep the thing from translating horizontally. But we also need a reaction here that will deal with this moment will create the secondary shear stress that we'll deal with later. I guess we could go ahead and calculate the value of that. If we go back to our book, it tells us that the distance from the center of the tube that is carrying the 50,000 newtons, we're only dealing with 25,000 because we're assigning 25,000 to each one of the red plates. So 25,000 has 100 millimeter, plus we're actually going to move this all the way down to the centroid of the weld group, which is that extra 10.4 millimeters. So 110.4 millimeters, that's where this number is coming from right here. All right, so I guess we can go back to Mathcad and say that we do V for the direct shear is just 25 kilonewtons. That one's pretty straightforward. M is 25 kilonewtons times a moment arm of 110.4 millimeters. It comes out in joules, which is a Newton meter. I'm going to do kilonewton meters though, so that we can probably have the same number that they have. I don't remember. Yeah, well, they actually put it in Newton meters later on, but that's okay. So for M, this value is 2.76 kilonewton meters. So now we have a system that's in equilibrium. Let's show that to you. So system that's in equilibrium, we have 25,000. Here's a 25,000 going the opposite way. This 25,000 creates a moment about the centroid of the weld group. This concentrated moment counteracts that so that it's not translating or rotating. So there's all of that. Now what they go and do is they solve for the direct shear. So that's just tau prime, and it is the shear force over the area. The shear force that's applied to the weld group is all located right here at the centroid of the weld group, is 25,000 newtons. So that's obvious how to put that in here. And the area is the area of the weld group, but we use the special area that is called the throat of the weld group because we're assuming when we're dealing with welds that they are going to fail by shear in the throat of the weld. And so to find the throat of the weld, or the area of the throat of the weld, you have this equation. So again, we're in case 4 on table 9.1. And, well, here's the actual area. We'll get to that one in a minute. I pointed the wrong thing. Here's the area of the throat of the weld group. So the 0.707 times H, that is calculating the throat size based on H, which is the weld size, 6 millimeters for us. And then there's 2B plus D, so that's basically this guy, and that guy. So let's go to Mathcad and plug our area in. So area equals 0.707 times H, which we haven't defined yet, times 2 times, oops, didn't put it in there, 2 times B plus D, not minus, equals, and we have to define H, so H is 6 millimeters. That's the weld size. It was given in all the weld callouts on all the fillet welds. There it is in meters squared. That's fine. So there's that. We have V. We have A. We should be able to do our direct shear. So tau, we'll call it P for prime, or lower subscript P, equals V over A. Comes out in pascals. Let's make it in megapascals. So 19.5 megapascals. Let's see if we're still on track with what the book is telling us. Yes, that's what they have. All right, so that is here. Up here, that's what they did. The 1280, that's the area that we just calculated. This is one thing I don't particularly like sometimes in these examples, is they don't use units on everything. That's why I'm putting it in Mathcad, so that I make sure that I keep up with the units. We've already done this part where we found the location of the centroid. Here, this is they're getting ahead a little bit. They're getting ready to do the secondary shear. And what they're doing here is finding all the little moment arms. So let's go back to here. So we have our, oh, I never wrote the rest of this out. So this was 1.281 times 10 to the negative third meters squared equals 19.5 megapascals. All right, so now we have that. So that direct shear is going to be on each location that we're interested in. And again, I said earlier that the endpoints of weld groups and the corners of weld groups are where you're normally going to be most interested. So we would have here, I'm just going to put tau prime, and I'm not going to write the 19.5 every time, just because it's going to get cluttery. It's going to be cluttery enough as it is. All right, so ideally, I draw all of those the same length, and they're vectors so that they're kind of useful as the picture themselves, but we didn't really go in and measure any of this. So if you do, like if you make everything to scale, then it does help rationalize what corners and locations are going to have the highest shear stress just by looking at the size of the vectors. But we're not being careful enough to do that, so we won't be able to do that. The moment arms that they dealt with now are, you go to the centroid of the weld group, and every point of interest, so we did point A, B, C, and D. Those are the points of interest for us. A and B are going to be similar as far as the stress, and C and D are going to be similar as far as the stress goes. But let's look at A. So the moment arm that they're going to calculate is basically this thing right here. And the secondary shear stress is going to be perpendicular like this. And we need to calculate that. So this is a right angle. And then here, let's call this G for centroid. I don't know, because I already have a C, so it's G. I think they actually might have used G in your book also. They did. No, they used O in your book. So in your book, they call that O. So DG is one moment arm for point D. And again, we would have a right angle with the secondary shear stress there. And this is the right angle. If we drew the CG and BG, they would be mirror images of this. So I'm not going to draw those just to keep it from being so cluttery, but they would just be a mirror image of this. And now we've got, and so these, notice these are all creating the same moment that this reaction is. So this reaction is basically happening through all of that moment. Same way as this this force is creating these direct shears. This moment is creating these secondary shears. And again, A and B are going to be mirror images. C and D are going to be mirror images. So we don't really need to worry about with C and D. We're just going to look at A and D. C and B, we're going to look at A and D. And so what they did is they found out the length of AG and the length of DG. So to do that, let's see if we can get in here. So I want to know this length. This length is 190 divided by 2, so that's 95. And this height is 56 minus 10.4, which is 45.6. And so I know here, I know two sides of a triangle, of a right triangle. So I can do the square root of the summation of the squares to figure out this length. So this length turns out to be, let's see, Mathcad. We'll call that AG equals the square root of 45.6 millimeters squared, whoop, not cubed, squared, plus 95 millimeters squared. 105.377. I believe your book rounds this off to just 105 millimeters. And then here we do a similar thing, except we have a height of 10.4, a base of 95. So almost the same equation. So this would be for DG. And instead of the 45.6, that height is 10.4. and it comes out to be 95.568, and they round it off to 95.6. All right, so we have our moment arms. We have the length of DG and the length of AG. So we have those two lengths. Next, what they go and do is they calculate, well, they draw a similar picture. They do go ahead and draw what's going on at B and C, but again, it's not exactly a mirror image because the forces are going the other direction. Well, the primaries are going the same direction, but the secondaries are going like a double mirror image. So it's mirrored and then mirrored again. But the magnitudes of the vector that these primary and secondary create, this magnitude is the same as that magnitude. So we don't really need to do all 4 points. I mean, that's often the case. Not universally, but it's often the case. So if you can't convince yourself that those are the same, then it doesn't hurt anything to go and calculate all the corners, and you're fine. Next thing we need to know, so again, they kind of skip ahead a little bit. This is what they're trying to do. They're trying to solve for the secondary shear, MR. Sometimes you see MC over J. MRR is the length of the moment arm that we just calculated. J is the polar moment of inertia, which you get from here. So we're in case 4, and we have this equation for JU. So this is the unit version, and then we multiply this times the throat size, and we will have J. So let's put this equation into Mathcad. So JU is equal to 8 times B cubed plus 6 times B times D squared plus D cubed. All of that divided by 12, and all of that, you subtract B to the 4th over 2B plus D. And it comes out in liters, but we're going to change that to millimeters cubed. And then to get J, we multiply 0.707 times H times JU. That one did come out in meters fourth. Well, let's do millimeters to the 4th. Actually, what did they use in your problem? Let's see. They use millimeters to the 4th because they want to create megapascals later on. So you can kind of see it. They don't. They put it right here. 707 times 10 to the 6. We got 7071 times 10 to the 6. So same number. Okay. Find M. We've actually already done that. This is where we went in and multiplied the 25,000 Newton force times its moment arm from where it was originally applied on the tube down to the centroid of the weld group. So that was 110.4 millimeters times 25,000. We already did that. So we did that. Here, they are calculating the secondary shear stress at A and B. So they're doing those together, saying that they're equal. And then C and D, saying that they're equal. Now, again, if you can't see that with it, drawn out, then you can do them all separate. You don't have to recognize that this corner is going to create the same secondary shear stress as this corner. You can do them independently and find out that they'll create the same. So MR over J, we need to do that. So tau, and we have to do this one twice. So the shear stress, direct shear stress, or we called it primary shear stress, we only had to do once. It gets applied equally over the entire weld group, but the secondary shear stress may not, because it has different moment arms. Maybe, so it will come out differently. MR over J. So for points A and B, but we'll just do A, M is the same. So 2.76 kilonewton meters R is the distance from the centroid of the weld group down to the point we're interested in, so AG, which was 105.377 millimeters. Your book just has this number as 105. And J is the number we just calculated, 7.071 times 10 to the 6th millimeters to the 4th. Okay. And if we plug that, let's go to Mathcad. So tau, and this is going to be the secondary, equals m, which we already defined somewhere, times, in this case we're doing R is the moment arm AG, so I'm going to put AG over J. Let's get it in megapascals. 41.132 megapascals. They, in your book, have 41.0. That's because they rounded some of these off, where in Mathcad you're not rounding anything really, at least not unless you go and tell it to round. And then that was for AG. We need to do this again for what would we call the other one? DG. So M times the moment arm DG over J. Put that in megapascals. Oh, we need a lowercase a. 37.303, and the book shows it as 37.3. So very close. Now, what you have to do next is you have to combine the primary and secondary together. And so that's what they're doing down in this area. They don't really go in and explain what they're doing here, but they're basically taking the X components, squaring those, adding them to the Y components, squaring those, and then taking the square root at points A and at point C, or A and D, or they did A and B together. They're the same thing, and then they did C and D together. They're the same thing. So they just said they're all equal. Okay. So what you do in this case, let's take, so it turns out that point D and C are the worst case scenarios. So let's look at that one. And if we do that one, then you should be able to also do this one. It's the same process, just different numbers. So at point D, what they're going to do here is they're going to create an x-axis and a y-axis, and they're going to find the x component of tau prime and tau double prime, add those together, and then they're going to find the y components, add those together, and do the squares, add the squares, take the square root of the sum of that. So let's write all that out. So let's move over. So at point D, you have in the x direction, you have just, well, let's do y first, actually. That's easier. Y component is only from the secondary shear stress. The primary is only exist in the horizontal direction, which I've just said is x, which is normal. And so the primary shear does not contribute to the y direction, only secondary does. So we just need the y component. So we just need this part. We just need tau double prime y. And that will be the y component of the resultant at D. And so what that means is we got to figure out this angle. And if you remember some of your identities or your geometry type things, then this angle and this angle are the same angle. I'm trying to write a tiny little alpha in there. I don't know if you can even see it, but that's a tiny little alpha and a tiny little alpha there for being the same angle. The way that we did this last time is if you know the rise over run of this, then just invert those, and that would be the rise and run of this one. This time I'm just going to say that this alpha is the same as that alpha. So if I know that one, which opposite over adjacent is tangent, so tangent of alpha equals the opposite side over the adjacent side. The opposite side is 10.4 millimeters. The adjacent side is 95 millimeters. Therefore, alpha is equal to, I guess we could do that in Mathcad or a calculator or something. I'm just going to do a calculator real quick. So I've got 10.4 divided by 95. Take the tangent, inverse tangent, 6.248 degrees. Let's see, in your book, they use 6.25, so that makes sense, 6.25. I don't even know. They actually call it beta in the book. I guess I should have looked at their nomenclature, but they call this beta, so that's fine. All right, so if I know that, then the y component of this guy is the cosine. So the y component of this, let's write it in red since I got red up there, equals tau double prime times cosine alpha, which is 6.25. So we calculated tau double prime, well, I never wrote it down, did I? At dg, so the one for this moment arm. Now this could confuse you a little bit because it is the smaller number. So this is for point D. It's 37. At A, it was actually 41. So the reason that we're going to be more interested in D is that in this case, the X component of the primary and the X component of the secondary add together. And down here, the X component of the primary subtracts from the X component of the secondary shear stress. So that's why point D ends up being the worst case. Now, you don't automatically know that because you don't know how much they subtract and everything. It still could be that this one's worse because it's a bigger number here. So you normally would have to go do both of these points, but since we already know the answer, we're just going to do the actual worst case point and then let you work out the other one if you really want to. So this guy is tau double prime 37.3 times the cosine of 6.25. Make sure you're in degree mode, and you get 37.08. So that's just tau y, megapascals. So that's the y component. Now, the x component at D, again, we're just looking at point D, is made up of, I'm going to add them together, even though maybe I should have drawn my x going that way, but they're both going the same direction to the left, and I'm just going to add them over here. They get squared in a minute anyway, so it doesn't matter if you have the negative sign. But if you're a stickler for that kind of thing, they're going to have negative signs that I'm going to leave off. So tau prime was 19.5. Plus, which really this should be negative plus a negative, which will be okay. The x component of the secondary thing. So for us, that's this little guy right there, tau double prime x, and that is tau double prime times the sine of alpha. So tau double prime again is the 37.3 times the sine of 6.25, and I get 4.06. So this one is 4.06 megapascals. So in your book, they just do that all in this, well, this line right here. So there's the 19.5, there's the m sine of alpha, there's the m cosine of alpha, or well, the tau double prime, I said m, tau double prime sine of alpha, there's tau double prime sine or cosine of alpha. So that's all that line, is doing this. And then to get tau, the shear stress, total shear stress, you do square root tau x squared plus tau y squared. And this would be at point D, and you would get the 43.9 megapascals. All right. And then you would do the same thing at point A, just to make sure. It does turn out lower. It turns out at 37 megapascals. So since we already know that answer, I'm not going to go through that again. But that's the process for getting through this. We may have gone through a little too many details, but at least this way you should be able to see and track all the numbers, where they're coming from and where they're going into the different equations for example 9.1. And I'm going to pop up the model just one more time so that you can get a look at what we were talking about here. So the point that we're interested in is this point over in this corner over here as our likely candidate for failure, or at least the one that has the highest shear stress. It's not a terribly high shear stress, 44 megapascals, so it's probably safe. Anyway, let me know if you have more questions, and I'll see you next time.